All right. Next topic is the epsilon-delta definition of a limit. It's kind of a weird little topic here. We're going to do it with a lot of really basic examples that you might not really get why we would even use this. But it's a nice little introduction. It's kind of one of those topics that's like old calculus. Like you can picture it being taught in a lecture hall like in the 50s or something. Like it's not used super often in like modern calculus, but you'll probably get, if you continue studying math in college, you'll probably get some old professor who still uses it or expects you to at least know what it is. So a little bit of exposure is going to be nice. So first of all, epsilon, your Greek letter epsilon, and delta, your Greek letter delta. I don't know why the epsilon showed up darker than the delta, but there you go. Okay. And we're going to write it out two ways, once in words, which is a little bit harder to follow, and then once in symbols. So first of all, your limit is x approaches c of f of x equals L means for any epsilon greater than 0, there exists some number delta such that f of x lies in the interval L minus epsilon, L plus epsilon. Okay. In symbols, what that means is the absolute value of f of x minus L is less than epsilon whenever 0 is less than that c value minus x is less than delta, with x not actually equal to c. Okay. And it's basically telling you, like, there's this window around c, okay, that's really small, such that it's less than this. Delta is usually a pretty small number. Epsilon is usually a pretty small number. There's going to be this small window around x that kind of gives us this small window around y. Okay, I'm going to show you graphically what that means, because that usually tends to help. Okay, so let's say that we have some function. I think there's a similar drawing in the PDF. Oops, I meant to change my color there. Okay, there's some function f of x, and we want the limit is x approaches c of f of x, and that limit that we want is L. Okay, so there is some c here that we're approaching. Okay, now epsilon is the value that you're given, and if you look up here, epsilon is that window around f of x. Okay, so we would have L here, and we'd want to be within L plus epsilon and L minus epsilon. It's kind of like that's your tolerance. Like, we got to be at least that close. Well, then I guess I should have changed colors on these two. I don't like using the same color all the time. Okay. If I follow this over, okay, then there's your, we're within, and you can see that on one side it's a little bit smaller. But as long as we are in c minus epsilon, delta, and c plus delta of c, we will capture that L within the tolerance that we want. And in fact, on this side, we get it a little bit closer, right? And again, you have to have, we can't go with the bigger one, because if we go to the left with that bigger delta, we wouldn't be within our tolerance on the left-hand side. Okay, we'd be out of that window that we want to get. Okay. Sometimes you'll see it like described as like there's a disk that we are within. The entire function is within that disk. This goes into non-functions too. But like this disk has a radius of delta, and whenever we're in that radius, we're close enough to our function. Okay, I'll give you a non-example because I think in this case that kind of works better. A non-example would be like if our function went like that. Okay, and at C, okay, let me erase some of this old stuff. Oh, I erased my function. That's okay. I'll draw it again. Okay. In fact, you know what? I'll redraw the whole thing. Okay, so if our function looked like this, and we wanted, this was our f of x, okay, and we wanted to approach C, and our L was here, okay, and we wanted to be within epsilon of it, and we have to hit it there, okay. You can see that within this C minus delta and C plus delta, we're not always within that tolerance, right? We're good except for right here. Okay, so we'd have to choose a smaller delta or epsilon to get within the range that we want. Okay, and that's the whole idea of a limit there. Okay, right now it's too big. We have to narrow it in. All right. Let's get to some problems because I think that might be a little bit confusing, but let's take a look at some problems so you just know how to work through a couple of these. Okay. We're going to start with an example. And again, you're usually given the function, and you're given C, and you're given epsilon. Okay. So in our example, f of x is 3x plus 2. We want to find delta such that this absolute value inequality is less than 0.01. Okay, when x minus 1 is less than delta. Okay, well, you can see if we go back up to what we did in symbols there, that means that this is epsilon. Okay, and then you can also see x minus, right, x minus c is the same as the absolute value, or c minus x is the same as the absolute value of x minus c, right? Okay. I'm just seeing if I wrote it wrong or if they just really did kind of mix you up. I think they did just mix you up on purpose here. Okay. But so then that is c. Okay. So they're finding the limit as x approaches 1 of f of x with an epsilon of 0.01. Okay. If we want, we can draw this out. It's linear, right? Okay. And we're approaching 1. Okay. And we want to be within 0.01 of that. Okay. So we can figure out, right? F of 1 is 5. So we want to be within 5.01 or 4.99. Okay. What they're asking you basically, how far can we get away from 1 and still be within that window from 4.99 to 5.01. Okay. So we need f of x. Oops, I'm sorry. Let me erase that. Oh yeah, the limit. Sorry. It's been a while since I've done this. Maybe even college. Okay, f of x minus 5 has to be between or within 0.1. Okay, so that means f of x has to be between 5.01 and 4.99. Okay, so we're basically just finding these endpoints. So 4.99 has to be less than 3x plus 2, or 5.01 greater than 3x plus 2. Okay, and the rest is just algebra then. 2.99 has to be less than 3x. You can use your calculator, or 299 over 300, right? It's less than x. Subtract 2 here. 3.01 is greater than 3x. So 301 over 300 is greater than x. So x has to be between 299 over 300 and 301 over 300. Okay, now you need to figure out, like, this would be your 301 over 300, and this would be your 299 over 300. It's asking you that distance from 1. Okay, so the answer here is going to be 1 over 300. Okay, as long as we're within 1/300th of 1, we are within 1/100th of f of 1. Okay, so we have found that window that is narrow enough for us to always be as close to f of 1 as we want. Okay, and again, when would that not happen? Well, when the limit doesn't exist or something. Okay, when we get too far away and we go out of that desired y window. Okay, but we just figured it out for this one. So for linear ones, you're gonna have that symmetry there where how far you go out left or right is gonna be the same. Okay. Let's do another one, just so again you can kind of see that setup. We are gonna do, let's see, find again delta. Sometimes it says delta greater than 0. Okay, such that absolute value of f of x minus L is less than 0.1 when absolute value x plus 4 is less than delta. Okay, so again, they give you your function. I suppose I should write it. That's a negative 6. Negative 6 minus x over 4. They give you your function. They tell you we're going to find the limit as x approaches negative 4, right? You get that from here. Okay. And we want to figure out how close we have to be to negative 4 to get our function within 0.1 of the true value. Okay. So again, and these are all going to be ones that are defined. These limits are defined. You get into some trickier stuff when the limit is undefined. Okay. But we are again we want to find f of negative 4, which would be negative 6 minus negative 4 over 4. So negative 6 plus 1, which is negative 5. Okay. So we want to have f of x minus negative 5 has to be between, or the absolute value has to be less than 0.1. So negative 6 minus x over 4 plus 5 has to be less than 0.1, or negative 6 minus x over 4 plus 5 has to be greater than negative 0.1. Okay. So let's see, negative 6 plus 5, that's going to be negative 1 minus x over 4 less than 0.1. Let's add that to that side and subtract from that side. So negative 1.1 has to be less than x over 4. So x has to be greater than negative 4.4. Okay, and then over here, negative 1 minus x over 4 has to be greater than negative 0.1. So negative 0.9 has to be greater than negative x over 4. We can divide by the negative and flip your sign. Okay, so x has to be, where I lost a negative somewhere, didn't I? Negative. Oh, this would be positive. Okay. And then that would be negative. Okay. And then, so I didn't want to flip the sign. Okay, so then negative 3.6 to be greater than x. Okay, so we're between negative 4.4 and negative 3.6. That center is at negative 4, negative 3.6, negative 4.4. So on this side, the delta we would need is 0.4. On this side, it's also 0.4. Okay, so again, you got that symmetry because it's linear. Okay, so you follow that same process every time. Okay, you set up this inequality, which is always f of x minus f of c is less than whatever that epsilon is that they give you. And you just kind of solve that inequality. You'll have a number in here, and you'll have a number in here. Okay, and then you always kind of figure out that interval in which side is going to be the shortest. And they've been the same so far because they're linear. All right. We're going to do one more that's going to end up not being linear. Let's see. Let's do find delta such that absolute value of f of x minus L is less than 1/4 when f of x equals x squared and L is the limit as x approaches 2 of f of x. Okay, so there's your C. So f of 2 is 4. So we want the absolute value of f of x minus 4 to be less than 1/4. Okay, so we want x squared minus 4, absolute value to be less than 1/4. So x squared minus 4 has to be less than 1/4, or x squared minus 4 has to be greater than negative 1/4. So over here, x squared has to be less than, let's add 16/4 to that, so it'd be 17/4. Okay. I'm just going to use a calculator to that. The square root of 4 1/4 is 2.06155. Okay, here x squared has to be greater than 3 3/4. So x has to be greater than 1.93649. Okay, so let's think about that interval again. Kind of like to draw it like a confidence interval almost. Or maybe a number line. Okay, so we know that we're centered at 2. We're going to go up to 2.06155, down to 1.93649. And again, any x values that are between those two numbers, when I square them, I will be somewhere between 4 1/4 and 3 3/4, which is that tolerance that's given to us. Okay. Now this is not symmetric because we have a it's not linear. Okay. And this distance is 0.06155, and this distance is 0.06351. Okay, so I have to pick one of them that will always put me in that window. So it's got to be the smaller one. Okay, so my delta will be 0.06155. Okay, so kind of think about it in your brain again. Okay, we have basically found an interval that's close to 2 that will put our function always close to 4. Okay, so that tells us that the limit as we approach 2 is going to be 4, mainly because we can keep making that interval smaller and smaller and smaller and get closer and closer and closer to 4, right? We can take that, if I want to redo this again and do 1/40th, I can still do all this work and it's going to get me closer and closer to 4, okay? So again, think about it. Doesn't have to make perfect sense right now, the whole theory behind it, but hopefully at least the mathematical process helps you a little bit and kind of get somewhat an idea of what we're doing. So good luck with that.